Okay, so this is actually an image of a fetus, and it shows the calcification of the skeleton. So you can see that the skeleton has already started to calcify, because when it calcifies, it becomes more dense. And so you can see those areas of that. Also notice that you can see the suture joints here. So you can see the coronal suture, for example. You can also see the lambdoid suture that connects the parietal bone to the occipital bone. And then this is a little bit iffy here. This would be the squamous suture that connects the temporal bone and the parietal bone. So you can also note, we'll talk about this, but we're going to next talk about what is happening at the ends of the bones that will allow the skeleton to grow. So we're going to talk about what is referred to as postnatal. So this is after a baby has been born, bone growth. Okay, so specifically when we're talking about the length of bones, we are talking about, we'll just emphasize long bone growth, and we're going to talk about the epiphyseal plate. So what type of tissue is the epiphyseal plate? Nobody remembers? So it would be hyaline cartilage. And it is also considered to be the growth plate. Okay, so the epiphyseal plates are hyaline cartilage that is then capable of undergoing cell division. So if we look at the end of a long bone, so I'm just going to draw my long bone here. This would be my hyaline cartilage. Okay, so that would be my epiphyseal plate. When we look at that plate, the way that it is going to grow is that the cells are going to divide, and they're actually going to push the epiphyseal plate away. So they actually push the epiphysis away from the diaphysis. And so we're just going to look at this area right here, right? So the area that is closest to the epiphysis is called the resting zone. So this would be like number 1. So this is the resting zone. So this would be the area that is closest to the end of the bone. And so the resting zone is just where the cartilage is not doing anything, right? So it is just being simply pushed away, because during the formation of growth, we want to maintain the same thickness of the growth plate. So the growth plate isn't going to become thicker, but it is actually going to maintain its thickness. So it's not going to get any thinner, okay? So this maintains the thickness of the plate. Okay. The second zone is what we call the proliferative zone. So what type of cell division do you think is involved in bone growth? Meiosis or mitosis? Mitosis. And so this is where the chondrocytes are undergoing mitosis. So it's not bone cells that are dividing to increase the size of the bone, but rather it is the cartilage that is undergoing mitosis. And so then from the proliferative zone, we have what is called the hypertrophic zone. So hyper means increased, and troph actually means feeding. And so this is where the spaces that the chondrocytes live in actually get larger. So we have an increase in the size of the lacuna. So that's hypertrophic. And then we have calcification zone. So this is hypertrophic zone, calcification zone. So this is where the matrix, instead of just being composed of collagen, we start to get the laying down of the calcium phosphate salts. So this would be where it starts to mineralize. And because the chondrocytes can't get nutrients directly across the surface of the matrix because the matrix has become hardened, then the chondrocytes die. So this is where we have chondrocytes dying. And then the final zone is the ossification zone. And this is where we get new bone cells that are then going to, if we think about the diaphysis, it is mainly the medullary cavity. So we're going to get the laying down of bone, but we're also going to get bone being eaten away. So in this particular instance, the bone cells lay down new matrix and also erode the old matrix. So in this fashion, the medullary cavity is maintained. So the medullary cavity also has to enlarge, so that's space. So in order to create that space, we have to have cells eating away during the ossification zone. Now, all of these zones exist right in here, right? So they are all existing right in that growth plate. So there is a microscopic image that shows this in your textbook. So this is just a diagram showing this is actually not an image of a microscope, but you can see here, this would be the growth plates, right? And what it's going to do is it's going to grow and it's going to push the epiphyses away and it's going to enlarge the diaphysis. So this is the diagram I wanted to show, okay? So this is the resting zone right here. And you can see that the way that the chondrocytes are arranged is they're actually stacked like plates. So this is different than in normal hyoid cartilage where they're kind of randomly distributed. So they're stacked like plates so that when they proliferate, they're going to increase the size of that plate. And then it's going to push the epiphyses away. Here you can see that the lacunae are getting larger, right? So notice proliferative stages is where the cells are dividing. So there's lots of cells. Here they're getting larger. Then the matrix is becoming calcified and the chondrocytes are starting to die. And then during the ossification zone, we get these spicules of tissue kind of hanging down like this. And so that is going to be where we form the new bone, but also where we erode the bone so we can increase the size of the medullary cavity. So there's another diagram in your book that shows this. So here the cartilage is growing, right there. Here the cartilage is being replaced by bone. And so you can see where the old bone was and where the new bone is. And the shape of the bone is different. And so the last thing that we have after that bone growth is we have what is called bone remodeling. So bone remodeling happens this is where the osteoclasts and the osteoblasts work together to change or to keep the shape of the bone constant. Okay, so osteoclasts, which break down the bone, and osteoblasts act to keep the shape of the bone constant. Right? So they have to actually break down, reabsorb bone here. So that's where the osteoclasts would be working. And then we have to add bone here, and that's where the osteoblasts would be acting. And all of this is actually due to bone cells that are in the periosteum. So in the periosteum, which is the connective tissue that surrounds the bone, we have these types of cells that act to kind of keep the bone in its proper shape. So that's what is referred to as bone remodeling. Okay. So one of the things about our skeletal system is that we can store calcium inside of our bones. And calcium is actually a really important mineral that is necessary for nervous system and also muscle function. And so when we look at the hormonal control of blood calcium, we have a set point. And I think that, let me just look, I think it's 90 milligrams or 9 to 11 milligrams per 100 milliliters. Okay, so this is 9 to 11 milligrams per 100 milliliters of blood. Okay. So if it goes above that, it is said to be hyperkalemia. So hyperkalemia is where your calcium levels are too high. And this can cause a problem for the nervous system and also the muscles. It actually makes the muscles less excitable if the calcium levels are too high. So it decreases excitability of the muscles. And then we can also have where the blood calcium is too low. This would be hypocalcemia. And when it's too low, this actually increases the excitability of the muscles. So we'll talk about the role that calcium plays in muscle contraction next quarter. Okay. Now there is a hormone that's really important in controlling our blood calcium levels, and this is called the parathyroid hormone. So this is abbreviated as PTH, parathyroid hormone. So the parathyroid hormone is in the parathyroid gland, and this gland is located behind or posterior to the thyroid. So it's actually on the posterior surface of the thyroid gland. So the gland is on the backside, so it'd be dorsal or posterior surface of the thyroid gland. And it is just little pockets of glandular tissue. So your thyroid gland is in your neck region. And so towards your vertebrae would be where the parathyroid hormone regulates. So this hormone is responsible for the activity of the osteoclasts. So let's say we have a low blood calcium level. This is the stimulus would be picked up by receptors. And then the effector here would be the parathyroid gland would then release parathyroid hormone into the blood. Okay, so then this is sent, let's just review homeostasis because that's actually one of your questions. So you could use this on your essay question. This is sent to the afferent pathway to the control center. And the control center in this case is the pituitary gland. So the pituitary gland actually can produce a hormone called the parathyroid stimulating hormone. And then that stimulates the parathyroid gland. So this would be my efferent pathway. So this is the parathyroid gland. So this is said to be the effector. So the parathyroid gland then releases the hormone. So we have the release in the PTH hormone. It goes to the bones. So remember, hormones are produced by endocrine glands and they travel in the circulatory system. So the parathyroid hormone would then bind to receptors in the bone and increase osteoclast activity. And then the response would that we increase the blood calcium levels. So would this be an example of positive or negative feedback? Negative feedback, right? Because the response of the osteoclasts, right, actually increases the calcium levels. So it would decrease the stimulus. So this is an example of a negative feedback mechanism. If it stimulated the osteoblasts to remove blood calcium levels, or to remove blood calcium and store it in the bones, then that would be a positive feedback, right? But this is a negative feedback mechanism. So in your book, they have a diagram of this. Okay. So your body, if you don't have enough calcium in it, it will take it out of the bone. So if your bones will actually get weaker if you don't have enough calcium. And we talked about that as a problem with osteoporosis, is not having proper calcium in the diet. So this is the parathyroid glands. And so they're just little bits of glandular tissue that sit behind the thyroid gland, kind of embedded in it. Now there is an antagonistic hormone. So one that has exactly the opposite. So it would actually decrease, if your blood calcium levels were too high, it would actually take the calcium out of the blood and put it into the bones. And so this is called calcitonin. So that's pretty easy to remember. But for some reason, they do not think that calcitonin is really significant in human physiology. For some reason, they don't think it's really all that important. They call it an orphan hormone. So we think that the parathyroid hormone plays a much greater role than calcitonin does in regulating normal levels of calcium. So this is produced by the thyroid gland. It might have other functions that we do not yet know of. Oops. Okay, so some things that affect your bone structure would be the mechanical stresses. And so there is a law, and I guess this is in physiology, called Wolff's Law. And this is that the structure of the bone is directly influenced by the forces that are applied to it. So the structure of your bones by the forces applied to them. So when we look at the structure of the bone, we notice that there are little protrusions on the bone. So there's like little rough spots, or there might be even little processes coming off of the bone. And those are directly due to the way that the muscles attach to the bone and the stresses that are applied to the bone. So the example that they give would be the femur. And so you notice that there are different parts to the femur, and the parts of the bone that kind of receive the most stress would be located up here. And you notice that that is where it is thickest. So when we have our body weight and we're supporting our body weight with our femurs, that is going to make the bone, the compact bone even, is going to be thickest at the end. And then you notice that we have these tuberosities. So we have these bony bumps, right? And this is actually where muscles attach. So anytime you see a structure like this, you're like, oh, there must be a muscle attaching there, because the force of the muscle is actually making that structure happen. Okay. And then the bone is at its thinnest right here. So this is where, if we looked at a cross section, there would be less compact bone or lamellar bone or lamellar bone, and there would be more spongy bone, because that is where the two areas, the compression, the forcing, pushing down, and the tension because of muscles kind of cancel themselves out. So that's the point of no stress. So that's going to be the weakest area right there in the bone. In your book, there's also a diagram showing how the diameter of the bone can increase due to activity. So if you're more muscular on one side of your body because you use that side of your body more, then that side of your body is going to have thicker bones. Okay. So we did talk about the importance of weight-bearing exercise on maintaining the density of the bone matrix, and increasing the strength of the bones. So like if people go, when they go out to outer space, right, there's no gravity and their bones start to become lighter. And so they have to do some exercises up there to keep their bone density high. Otherwise, when they come back down to earth, they're at a much greater risk of breaking a bone because their bones have become weaker. Okay? So remember that our bones are living tissue and they're constantly remodeling due to the forces that are applied to them. So you can't think, oh, I had healthy bones as a child, right? And think that you can lay around in bed a lot and still have healthy bones. Okay, so we're going to talk about bone repair. So the first thing we're going to talk about are types of fractures. And there are some different types that are described in your book, but these are the three different types that I am referring to on your sheet, your handout. So on your review sheet. So the fractures, you can have displaced versus non-displaced. So this is how the bones line up after you have broken them. So if the bones line up and they're in line with one another and you don't have to reset them and you don't have to put pins in them, then it is a non-displaced fracture. But if the bones come apart and they come away from each other, then you have to set the bone, right? You have to put it back in place. And so if you do not set a bone, then what will happen is that the bone will try to repair itself and it won't look very pretty. So this is an example of a bone that was broken, right? This is the femur, and there's where the bone was broken. That is kind of near its most weakest point. Actually, it would be up here, sorry. This point down here would probably also be, oops, a little weak, okay? And then you'll notice that this actually healed itself, but not very well, okay? So that would be the bones didn't get put back together properly, the ends of the bones. Okay. Let's make, can I just delete those? Yeah. Okay. We also have the complete versus incomplete. So this would be whether or not the bone has completely fractured all the way through, or whether it just has a crack in it. And one of the things that's really interesting about children is that their bones are a little bit more flexible. And so sometimes they actually get wrinkled fractures. So their bone actually just wrinkles a little bit and it doesn't even crack. It just has a wrinkle in it. And then they really don't do much for that. They just kind of let it re-heal itself. But complete versus incomplete. And then this is really important. This is the compound So this would be that it is open versus simple, which is closed. So if the bone sticks out through the skin, that is much, much more dangerous than one that stays inside the body, right? For obvious reasons. Primarily, you have a great deal of risk of infection, right? If the bone actually comes out through the surface of the skin. So in your book, there are also some other examples. So one of the interesting ones has to do with where you get compression, where the bone is crushed. And so this one is really interesting because when we're going to start talking about the spine, but old people sometimes have compression fractures in their bones, in their vertebrae, because those bones have become weakened due to osteoporosis. And so the reason why they might be hunched over like this, it could be due to that they have, and they have kyphosis like that. It could be due to the fact that they have actual crushed compression fractures in their bones. Again, these bones are more brittle. So this would be the type of fracture that you might see in an old person. And obviously that's a lot harder to repair than a fracture where you just have one plane of breakage. Okay. Here is a spiral fracture where you have twisting forces applied. So that is common, what is found in sports. And then this one is a kind of a dangerous fracture to have if you are a child and still growing, because if you break that hyoid cartilage plate, then it might be that that bone will not grow. So the bone will cease growing, and that could be a big problem. Okay, so that's where you have a fracture at the epiphyseal plate. This is what is called a green stick fracture, and this is very common in children. So their children have more of the collagen matrix and less mineralized matrix, so their bones are not as brittle as older people, and so they get what would just be like a little wrinkle in the surface of the bone. Okay, so let's look at the stages of bone repair. So these would be stages of bone repair. I think I mentioned this before, but it is bones that have fractures in them, not joints. So you can't say that you fractured your hip. It is actually a fracture in the femur, right? So joints don't fracture, but bones do. Okay, so the first thing that happens is you get a hematoma. So this is a blood clot. Oops, blood clot. And this actually causes the cells in that area to die. So the bone cells start to die. We also have macrophages that go in and clean up the area of damage. Then we get what is called a soft callus. So the bones form these calluses, and the first one that they form is a soft callus on the bone. And that is called a fibrocartilaginous callus. So we need to repair the bone, but the first thing we need to do is we need to lay down connective tissue, right? So bone can't form on its own. It has to go through a stage like the hyoid cartilage modeling, right? Where it actually goes through a stage where you get that modeling. And so this is where we get fibroblasts laying down collagen fibers. And then we get, this is sometimes referred to as the soft callus. The third one is the bony callus. And so this is where we start to get bone being laid down. And the first type of bone that is laid down is the spongy bone. So spongy bone is produced by what are called osteogenic cells. So this is another term for osteoblasts. Right, so osteogenic means that they are bone-forming cells. And then the last one is that idea of the bone remodeling, right? So we want to get rid of that hard structure on the outside of the bone. So the bony calyx is reabsorbed, or callus is reabsorbed. So if we look at a diagram, or actually an X-ray of this, you can see in the X-ray, this is fracture repair. So this would be in the wrist area. This is a common fracture that you get when you fall with your arm outstretched. And I think it's called Colles fracture. And you can see that the callus is being formed around that area of break. Okay, and then you can see the spongy bone being laid down between the two parts of the bone. Okay, so we're going to watch an animation of this healing process, video animation, short little video. Oops. Let me. So you can see the collagen fibers underneath, and then that represents the osteoblast that is laying down the mineralization, the matrix. And then they become mature osteocytes that reside in the bone.
Music makes this feel like 1,000 times more dramatic than it should be.
Yeah, it is. But actually, it's quite amazing if you think about it. That your bone is living tissue and able to regenerate itself. So that's spongy bone. The outside is the compact bone. So these are the osteoclasts that are releasing acid. It's actually an acid and an enzyme that allows the matrix to be reabsorbed. So has anybody ever had a bone fracture where they could actually feel the callus? So you could actually touch the bone and feel it. Supposedly you are able to. Okay. So we are moving on to the next chapter, which I believe is chapter 7. So we're going to talk about the skeleton. And the first thing that we're going to talk about is the axial skeleton. So this includes the skull, the vertebrae, right, the rib cage, as well as the sacrum, the coccyx, and then also the hyoid bone. So the hyoid bone, we'll talk about, it actually sits in the region of the neck. It's not technically part of the skull. So that would be the axial, and you can think of it as the center axes of our body. Then we have what are called the girdles, which attach our appendicular skeleton, which would be the arms and the legs, to the axial skeleton. So one thing that the axial skeleton does is it is protection. It's also support. So the stacking of the vertebrae allow us to support our weight against gravity. And then it is also responsible for movement, as in the rotation of the head, the flexion of the spine, and the extension of the spine. We could also have side bending, which is referred to as lateral flexion. So we'll talk more about that when we get to the different parts of the skeleton and when we get to the joints. Okay, so as a review, we can talk about the bones of the skull. And so what is this bone right here? That's the frontal. Is there one or two of those? Just one. How about this one back here? Occipital. And remember that these are suture joints right here. This is the squamous suture joint. And those are relatively immovable. So they're fibrous joints. So collagen fibers connect those two bones, except when we're babies, when the bones have a little bit more mobility because they're growing and the sutures have yet to fuse. Okay. This bone is called the temporal bone. And it has some bone markings. So one of your essay questions talks about, give some examples of bone markings. So the temporal bone is really weird, flat, but also irregularly shaped bone. So does anybody remember what this bony protrusion right down here is called? So it's that bump behind your ears. This is called the mastoid process. And one of its functions is that it is the attachment point for a muscle. So this is where a muscle attaches. Hence the rough, the thickened shape of it. And this is actually a muscle that allows us to bring our chin to our chest, so that when it contracts, it shortens and it draws the head down. So that would be an example of a process. This is the outer ear, which is the external acoustic meatus. And its function would be that it's a hole, but its function is that it allows sound waves to move into the skull where your inner ear resides. So where your cochlea, where you're able to absorb sound energy, that's the opening for sound waves to enter the ear. We also have the mandible and the maxilla. And there is a joint here which is really important. This is called the TMJ joint. So the temporal mandibular joint, right? So one of your questions, I think, has to do with, I didn't put jaw in there. So number 10 on your essay questions has to do with joints. So these are joints that we are going to be looking at this week in lab and next week in lab. So we actually have 2 more labs before you have to have all of the bones and the bony processes identified. Okay. Okay, we also talked about sinuses. And so you need to be able to identify the different sinuses. And so these have a variety of functions. So these are in the skull. One thing that they do is that they help to humidify the air. So when we breathe in the air, when it comes into our lungs, we want that air to be semi-humid, because otherwise our lungs are going to dry out, because the lining of our lungs is a respiratory membrane that has to be maintained moist. And so, for example, the ethmoid sinuses allow for that. The other thing is that it actually helps to filter the air, or filter air of debris. And then it also is resonating chambers. So people that have like nasal, they're resonating, they're using their nasal cavities to change the tone of their voice. And then they also help to lighten the skull. So you can see that we have 4 different chambers, and you can see that one of them here in green is composed of many little bones. And does anybody remember what that sinus is called? The one that's many little bones. And if you have sinus surgery, this is where they go in, up through your nose. and they would take those bones out. Anybody know? Starts with an E. Ethmoid. So these are your ethmoid sinuses. Okay. The one that is way in the back is the one that is the sphenoid sinus. We also have sinuses up here in our frontal bone. And so that's an easy one to remember. Those are the frontal sinuses. And then we have them in our cheekbones. So our upper jawbone. So these are the maxillary sinuses. So one of the really interesting things about our sinuses is they do not drain very well. And so they believe that when our ancestors were down on all fours, their sinuses drained. And you can kind of experience this if you're a person that uses sinus irrigation. So doctors even recommend this. My sinus doctor recommends that you irrigate your sinuses with salt water, warm salt water, which means that you just put warm salt water up your nose, right? And then it kind of drains out. But it doesn't drain out very well if you're standing straight up. So it's like I put salt water up my nose and like my sinus is filled with salt water and they're just still filled with salt water until I go like this. And it's really embarrassing if you do this before yoga, because then all of a sudden all that salt water will just kind of come out, right? So as soon as you bend over, your sinuses drain, right? It's like a neti pot. The new thing is the squeeze bottle. The squeeze bottle, yeah. And that's supposed to actually help tremendously because our sinuses just do not drain properly because we are in this vertical position. They weren't designed that way. They drain only if we're kind of tipped over like this. Okay. So for the quiz next week, you need to be able to identify these sinuses. Okay, so this is a diagram showing the hyoid bone. And so the hyoid bone is really interesting because it is believed to be a remnant of a gill. So when we are in the fetus stage, right? Oops. When we're in the fetus stage, we have pharyngeal gills. So the pharynx is the common opening to your digestive and your respiratory tracts. And so it is like the back of your throat before the back of the throat goes into the trachea or the esophagus. So that's the back of the throat. And then we have these gills. And so this is thought to be a remnant of a gill bar, which fish have. Interestingly, in mammals, they think that our other gill bars actually became our internal ear bones. And so they have migrated up and become incorporated into the skull. So if you look at this bone, it has processes that attach it to the temporal bone. You don't need to know that, but there would be like, this is attached ligaments to our temporal bone up here, the styloid process of the temporal bone. And this is also the base of the tongue. So this is a movable base for the tongue. So the tongue kind of attaches, and that hyoid bone moves up and down. It is also connected to our larynx, which is our vocal cords, or to the it's connected to the thyroid cartilage. So if we look at a diagram of this in our body, this is where your thyroid bone would sit. So it's above where you feel the cartilage of your trachea. The hyoid bone would sit up there. Okay, so we're going to start talking about the vertebral column. I have handouts, but I'll give them to you on Monday. So when we talk about the vertebral column, we can talk about the arches. So we can talk about the way that the column bends. And so when we look at the structure, I'm just going to draw it here from the side. So this is the neck region. Here's your thoracic region. Here's your lumbar region. And here's your sacrum. So this is the cervical region. Okay. So looking at it from this direction, okay, it actually makes a big difference if you're looking at it from the front or the back. So this is the posterior. So this would be posterior. Okay. So it kind of goes in. So it is said to be concave. So you don't want your neck to be completely straight. You want there to be kind of a normal concave arch in the back of your neck. Okay. Then this is the thoracic region. And this is not concave, it's convex. So if you think about your back, kind of sticks out. So this is the normal arch for the back. Then what do you think this region is right here? Lumbar. So the lumbar region is just like the cervical region in that it is concave. And then this is the sacral. So this one right here is the sacral region, and it is convex. So it is like your sacrum and your tailbone, they kind of come out and then back in, right? So your tail is tucked under. So these are the normal spinal arches. Now, sometimes we can have abnormalities. So we can have what is called kyphosis. And this is where your cervical vertebrae actually start to come the other way, so they become concave. And then you get an exaggerated thoracic. So the kyphosis, I have pictures of these. The kyphosis would look like this. So you have the thoracic or the cervical is kind of not as indented, and then you get a big hump on the back. So that's kyphosis. And then we have an exaggerated lumbar region, and this is what is called lordosis. So this could be due to probably in this girl that she's got kind of a big belly, right? And so she's kind of sticking her bottom out in order to balance the belly on the front. And so lordosis happens when people get pregnant too, or when they get a big beer belly, right? They have to balance themselves out so they lean back, and then you get an exaggerated arch in that region. So what is this one where the spine has an arch to the side, which would be a lateral instead of convex or concave? What is that called? Does anybody know? Scoliosis. Okay. So, and then this one's kyphosis. And I mentioned before that kyphosis could be due to the fact that they've had compression fractures in their vertebrae that are making their vertebrae kind of compress down and stick out more like that. Scoliosis is generally due to you're generally born that way, although you can get little minor types of scoliosis if you always carry your heavy backpack on one side, then that can cause some abnormality in the spine, but not this much. Okay, so it's genetic and birth defect. Okay, so I will stop there for today, and we'll continue our discussion and review of the skeletal system on Monday. Yes?
You want us to do the joints?
Is that this next week? You know, I think I'll just move it because we haven't started joints. So I'll move it to the next weekend. Yeah, thank you for letting me know about that. I forgot all about it.